Hello and welcome to this class. In this class, we are going to look at acid-base theories. They are theories that are formulated to explain the meaning and concepts of acid and bases. There are three, and we have Arrhenius theory, Bronsted-Lowry theory, and we have Lewis theory. So we'll explain each of them one after the other, and we start with Arrhenius theory. In Arrhenius theory, this theory tells us that an acid is a substance that dissociates in water to give us hydrogen ion as the only positive ion. An acid dissociates in water. It dissociates in water to give us hydrogen ion. That is for Arrhenius. So hydrogen ion must be present and water must be present for a substance to be called an acid according to Arrhenius, because the substance must dissociate or break up in water to produce hydrogen ion. Now, examples. When we have HCl breaking up in water or dissociating in water to give us hydrogen ion plus chlorine ion. Now, because of this hydrogen ion that is produced when this HCl is dissociated, we call HCl an acid. We say that HCl is an acid. Now, when we have H2SO4 breaking up or dissociating in water to give two hydrogen ions plus SO4 2 minus. Now, because of the hydrogen ion that is produced when this H2SO4 is dissociated, we say that H2SO4 is an acid. When we have HNO3 dissociating in water to give hydrogen ion plus NO3 minus. Now, because of the hydrogen ion produced when this substance is dissociated in water, we say that HNO3 is an acid. Now, when we have ethanoic acid, when we have CH3COOH dissociating to give hydrogen ion plus CH3COOH. Now, because of the hydrogen ion produced, this substance is an acid. So we have many of them. Any substance that when it dissociates in water produces hydrogen ion, according to Arrhenius, the substance is an acid. Now, for a base, according to Arrhenius, a base is any substance that dissociates in water to give hydroxyl ion as the only negative ion. So for Arrhenius, a base dissociates in water to give hydroxyl ion. Now, when we have sodium hydroxide dissociating in water to give hydroxyl ion plus sodium ion. Now, because of the hydroxyl ion produced when this substance is dissociated in water, then we say that this sodium hydroxide is a base. When we have potassium hydroxide which dissociates in water to give hydroxyl ion plus potassium ion, then we say that because of the hydroxyl ion produced, potassium hydroxide is a base. Also, when we have calcium hydroxide, calcium hydroxide, which dissociates in water to give two hydroxyl ion plus calcium ion. Now, because of the hydroxyl ion produced, then we say that this is a base. So any substance that generally, when it dissociates in water, produces hydroxyl ion is called a base, according to Arrhenius theory. Now, it is important for us to note that for Arrhenius, water must be present. Water must be present for any substance to be regarded as an acid or a base. Water must be present for any substance to be regarded as an acid or a base, according to Arrhenius theory. Now, we have limitations with these Arrhenius theories. Limitations that we have there. Now, the major limitations we have with Arrhenius theory is that, number one, it cannot explain the acidic properties in non-aqueous environments. It cannot explain acidic properties in non-aqueous environments. That is, when there is no water, it cannot explain why some substances still exhibit acidic properties. Like when we have dry HCl, that is HCl without any water added to it, but it still exhibits acidic property. Now, Arrhenius theory cannot explain this behavior, why the HCl should be exhibiting an acidic property without being in water. Other acids also, when they exist as dry substance, they also exhibit acidic property even though they are not in water. So we have H2SO4 also exhibiting acidic property without being in water. So Arrhenius theory cannot explain this behavior. Then number two thing is that Arrhenius theory cannot explain acidic properties of certain substances that do not produce hydrogen ion. So it cannot explain acidic properties of certain substances that do not produce hydrogen ion. Example, when we have AlCl2, this substance has acidic properties, but when we dissociate it in water, it does not produce hydrogen ion. So Arrhenius theory cannot explain why this substance acts as an acid when it cannot produce hydrogen ion when dissociated in water. Also, it cannot explain the basic properties of some substances that do not produce hydroxyl ion when they are dissociated in water. Number three, it cannot explain the basic properties of substances or substances that do not produce hydroxyl ion when dissociated in water. So when we have ammonia, when it is dissociated, it doesn't give water. So we find it difficult to use Arrhenius theory to explain why this substance acts as a base when it does not give hydroxyl ion when dissociated in water. So these are limitations of Arrhenius theory. So it cannot explain the acidic properties of so many substances. So to overcome this, another theory was put forward by Bronsted-Lowry. So we now discuss Bronsted-Lowry theory. Bronsted-Lowry theory. Bronsted-Lowry theory now talks about acid and bases as their ability to donate or accept protons. For this theory, an acid is a substance that donates a proton. An acid is a substance that donates a proton. And what is a proton? We know that hydrogen ion is positively charged, and because it is positively charged, it is always regarded as a proton. It has no electron in its hydrogen ion. So when we are talking about a proton, someone could easily use hydrogen ion to talk about a proton, since it does not have any electron, but it's only the proton in it that exists. So according to this theory, an acid is essentially any substance that donates a proton, that donates hydrogen ion. An acid is any substance that donates hydrogen ion. So when we have HCl, plus ammonia, now we can now explain the behavior of this ammonia acting as a base when we define acid as a substance that donates a proton and a base as a substance that accepts a proton. Now looking at this equation, at this reaction, HCl donates this hydrogen to this ammonia to give NH4 plus chlorine ion. So because the HCl donated hydrogen ion, it is an acid. The hydrogen ion is a proton. Anytime they are talking about hydrogen ion anywhere, or anytime any person is talking about a proton, you can as well use hydrogen ion to represent the proton being talked about. So because this HCl has donated hydrogen ion, we can say that it has denoted a proton. So, and this ammonia has accepted the hydrogen ion, which means that it has accepted a proton to itself. So the ammonia is now acting as a base, while HCl is acting as an acid. So this explains why this ammonia is acting as a base even though it does not produce hydroxyl ion when dissociated in water, according to Arrhenius theory. So with Bronsted-Lowry theory, we see that this is a valid base since it accepts a proton from an acid. So we have other examples. When we have H, we have HCO3 minus plus H2O. Now this will give us H2CO3 plus hydroxyl ion. Now looking at this, which one is acid and which one is a base? Now it is also important for us to note that a substance can only act as an acid or a base if it donates a proton or accepts a proton, and we find out whether it has donated a proton or accepted a proton from a reaction. Therefore, we can only show that a substance is an acid or a base only in a reaction. If we don't see the reaction, we cannot determine whether the substance is acting as an acid or a base. Just like in Arrhenius theory, water must be present for us to know whether a substance is acting as an acid or a base. In Arrhenius theory, the reaction must be shown, that the equation for the reaction must be shown for us to know whether a substance is acting as an acid or a base. It is only when the equation is shown that we can see whether the substance is accepting a proton or it is donating a proton. So what this thing means is that sometimes a substance that has acted as an acid somewhere can act as a base in another place. So it all depends on the reaction that the substance finds itself. So for instance, in this example, the HCO3 is acting as an acid because it's acting as a base because it is accepting hydrogen ion from water. It's accepting hydrogen ion from water. So we have one hydrogen here. Now it's accepted another hydrogen to become H2CO3, this place. So because of this, it has accepted a proton. So the one that accepts a proton is a base. So this is acting as a base. Now, why this one has reduced its number of hydrogen, that is, it has donated one of its hydrogen atom as an ion. So it has donated a proton to another component. So this water is acting as an acid, while this HCO3 is acting as a base. So this is just by looking at the reaction. Then we look at the one that is donating a proton and the one that is accepting a proton. Now, a quick guide is that to know which one is actually an acid or a base, now we look at the left hand side and the right hand side. The one that the hydrogen ion has increased, that one is acting as a base, but the one that the hydrogen ion has reduced from left to right. That one is acting as an acid. Like HCO3, it has only one hydrogen in the left hand side, but in the right hand side it now has two hydrogen atoms, which means that the hydrogen atom has increased. So the one that the hydrogen atom has increased is acting as a base. So this one is now a base. Now the one that the hydrogen atom has reduced is acting as an acid. So water here, the hydrogen atom has reduced from 2 to 1, so it is acting as an acid. Now what we find out is that the one that is acting as an acid in the left hand side, when it comes to the right hand side, it will be acting as a base. And the one that is acting as a base in the left hand side, when it comes to the right hand side, it will be acting as an acid. So we call this a conjugate acid and conjugate base. A conjugate acid is formed from a base. So when the conjugate acid reduce its number or donate its hydrogen atom, it becomes a base. And when a conjugate base accepts a proton or a hydrogen atom, it becomes an acid. So what it means is that this is a conjugate acid, conjugate acid, while this one is a conjugate base. A conjugate acid is from a base, while a conjugate base is from an acid. So other examples of Bronsted-Lowry acids and bases, we have HCl plus NH3, giving us NH4 plus this. Now, looking at it through Bronsted-Lowry theory, this is an acid because it donated the hydrogen ion to ammonia. So the ammonia accepted the hydrogen ion, and the hydrogen now increased from 3 to 4, while this one has reduced its hydrogen ion from 1 to 0 here. So this ammonium is from a base, so it is a conjugate acid. Ammonium is a conjugate acid here, while chlorine ion is a conjugate base because it is from an acid. Then another example is when we have HCO3 minus. No, when we have HCl plus water, now what we see is that this will give us hydrozonium ion plus chlorine ion. Now this HCl, it has reduced its hydrogen atom from 1 to 0 here. while water has increased its hydrogen atom from 2 to 3. So here, water is acting as a base since it is accepting hydrogen atom. So we can see that in Brothelori theory, a substance can behave as an acid somewhere and as a base in another place. Now, there are few substances that do this, and any substance that has this property of acting as an acid somewhere while acting as a base in another place is called an amphoteric substance. Amphoteric substance. Amphoteric. Amphoteric substance. A substance that in one condition they act as an acid, while in another condition they act as a base. That is an amphoteric substance. Example is water. Example of an amphoteric substance is water. So let me talk about this again. This is an acid, this is a base. Now this is a conjugate acid because it's from a base, while this one is a conjugate base because it is from an acid. Now this Brothelori theory has a limitation, and the limitation of this theory is that only a species that contains at least one hydrogen ion can act as an acid. The readily available proton for reactions is hydrogen ion. So it means that any substance that does not contain hydrogen ion will not act as an acid according to Brothelori theory. So, but we know that we have so many substances that they act as an acid, but they don't have hydrogen ion. So, something like the same AlCl3 that we discussed before, it has no hydrogen atom, but it acts as an acid. Therefore, we can say that this brings a limitation to Brothelori theory. Now, to overcome this, another theory was put forward by Lewis. Lewis theory now. Lewis theory. Now, according to Lewis, an acid is a substance that accepts electron, while a base is a substance that donates electron. The difference between Lewis theory and Brothelori theory is that Brothelori theory is talking about proton donation, while Lewis theory is talking about electron donation. And in Brothelori, it is acid that donates. It donates proton, while it is a base that accepts proton. But in Lewis theory, it is the base that donates. It donates electron, while the acid accepts the electron. So that is it about Lewis theory. In Lewis theory, we have an acid that donates electron. Then we have a base we have a base that donates electron, and we have an acid that accepts electron in Lewis theory. In Lewis theory, we have a base donating electron, and we have an acid accepting electron. Now, for instance, in this reaction of Bf3 plus F minus, this is boron fluoride, boron trifluoride. Now, when it reacts with fluoride ion, we have boron tetrafluoride, Bf4. Now, in this reaction, this is negatively charged, so it is donating the electron that it has here. Negatively charged means that it has excess electron. Now it is donating it to this boron, which is lacking electron, to become Bf4. In Lewis acid and bases, the structure of the acid and bases is important for us to know whether it is donating or accepting electron. So for this boron, we have boron is, we have fluorine here, and fluorine here. Now there is a positive charge here. It is lacking one electron, so this donates electron to it to form the boron tetrafluoride. So this is acting as a base. This is acting as a base, while this one is acting as an acid. This donating electron is a base, while this accepting electron is an acid. Another example is when we have CH2O plus water. Now this gives us CH2OH. Now in this reaction, this substance accepted electron from water, so this is acting as a base. This is acting as a base, and this is acting as an acid. Again, when we have H2O plus this gives us H3O plus. In this is positively charged, which means that it wants more electron. The electron is supplied by water to become hydrogenium ion. So this is an acid since it's accepted electron, while this is a base which donated electron. Another example, when we have NH3 plus BCl3, this will give us NH H going to complex with B, Cl, Cl, Cl. Now this is acting as a base while this is acting as an acid, which means that this one has excess electron that is donating to this. Now this accepted electron for the compound to become this. So this is an acid, this is a base, and this is an acid. Another example is when we have OH minus plus CO2. This substance will give us HCO3 minus. Here, this has negative charge, which means that it has excess electron, which it now donates to CO2 for it to become this. So this that has excess negative electron that is donating is a base, while this one accepting it is an acid. So